Okay, so now that we understand the basics of complexation with EDTA and metal ions in solution, we can use that knowledge to understand and predict how one would go about computing different concentrations of metal ions at different points in an EDTA titration curve. And so as I mentioned before, EDTA titrations are super common. They're common in sort of environmental chemistry applications. It's one of the most robust ways to determine what's called the hardness of water, um, which is sort of a proxy for calcium and magnesium ion content in water. It's also used almost more frequently nowadays in biological applications where folks are studying the impacts of metal ion concentration on the behavior or function of different biomolecules. And as I mentioned, Dr. Nina Grover uses this to study the interaction of metal ions like calcium and magnesium with strands of RNA and specific structures of RNA, but it's also really common to study and understand sort of the dynamics of metal ion transport across cell membranes, and a variety of other things. It's sort of a tried and true robust method. The big assumption or big approximation we're going to make here, which is almost always going to be true, and I mentioned this in a previous video, is that the stoichiometry between EDTA, whatever the form is, but specifically the Y4 minus form, with any of the metal ions is always going to be 1-to-1, which makes it really easy. There's always going to be a 1-to-1 binding stoichiometry there. At the same time, we're almost always going to be treating the EDTA equilibrium from the perspective of the Y4 minus species, but we know well now that that's an incomplete description. Not that it's inaccurate, it's still true, right? If you compute one equilibrium, that equilibrium still has to be true, even if you don't explicitly compute all of the other ones. But the convention is to treat it from the perspective of Y4 minus, and that's also the convention from which the log Kf values are computed for specific metal ions. So we're going to compute several different regions as we have already in previous titration examples with acids and bases. The general EDTA titration curve is going to look like the one on the left. We're going to compute our own, but this is the generic version of that. And there's really three major regions. There's the region where we have excess metal ion. Notice the y-axis here. This is P metal ion concentration. So we're going to do a titration of calcium ion in solution. So this would be P calcium. You might not have ever seen P applied to anything but hydrogen ions, but there's no reason it can't, really. It just means negative log of. And so since it's negative log of the concentration of the metal ions, then high concentrations are down at small PM values or P ion values. So that's the region of excess metal ion in solution, meaning you haven't added a stoichiometric amount of EDTA or 1-to-1. We have region 2, which is the equivalence point, so you've added exactly molar equivalent amount of EDTA to completely bind up all the calcium or whatever metal in solution is, and we're always going to assume 1-to-1 here. And then we have the third region, which is excess EDTA, so we've added stoichiometric excess of EDTA in solution. So first step before we move into any one of these regions specifically is to compute our conditional formation constant. So remember from the previous video that K prime F, or conditional formation constant, is the original formation constant for the reaction as written, where we have our metal ion plus Y4 minus, that's the convention, makes the bound complex. But that would be our normal Kf, and our conditional that we denote by this prime here is one that is multiplied or adjusted by the fraction of Y4 minus that's present at the pH that the solution is at. In this case, and as I mentioned previously, most EDTA titrations are conducted in systems where the pH is 10 or above, and they're buffered at that pH to ensure that throughout the duration of the titration, the pH isn't changing. Because if it's changing, then the equilibria are changing in real time, which would lead to more systematic error in the system. So often in a problem or in reality, you'll see that the EDTA titrant is buffered at pH 10 or 10.5 or 11. And remember, the reason for that elevated pHs just because that's where Y4 minus is most abundant. And so we can grab from, the first thing we can do is grab the alpha value, the fractional value of Y4 minus at that pH. And so if we jump down to 10 here, we can see that it's at 0.3. So we can insert a value here for 0.30, and then we can also look up the standard formation constant of calcium. So we can jump down and find calcium on this list, and it's right there, and that's 10.65. And so we can, and these are log KF values, so this would be 10 to the 10.65 for the real KF value. And so that, if we compute that, would give us our conditional formation constant that's been adjusted for the fraction of Y4 minus. That gives a value of 1.3 sub 4 times 10 to the 10, so that's a huge value, roughly 13 billion. So, of course, as I mentioned several times before, formation constants for EDTA with metal ions are almost always large, especially when the ion charge is in excess of 1 and the ions are fairly small. So we always assume these things go to 100% completion, and we always assume they're binding in 1-to-1 stoichiometry. So I'm going to take this value, I'm just going to put it up top out of the way, or maybe I'll put it in the bottom out of the way, just so that we can have some space to compute the rest of these regions. All right, so second thing we need to do, as we've done in all titrations preceding this, is find the volume at equivalence. So what volume of the EDTA solution is required to deliver exactly equivalent number of moles of EDTA to whatever the metal ion moles are in solution. And so we can do this with M1V1, or we can do this dimensionally. You've seen this several times, so I'm going to just write that out. So that gives me 25.0 mils as the volume added to reach equivalence in this problem. Note that the curve that I have here is not the curve that we're computing. This is just a reference point. So here the VE would have been 50. I don't want you to be confused. So the example we're doing is different from the curve, but the curve will nominally be exactly the same shape. It's just the values will change slightly with our specific example. So I'm going to grab that, write it down below, and then clear up some space again. So we'll start with region 1, where we have excess calcium. So we have not added enough EDTA to the solution to completely complex it out. So we're pre-equivalence at this point. And we know that because we just determined our equivalence volume to be 25. And in this example, we're asking what the calcium concentration would be in solution. The free calcium concentration would be after we added 5 mils of the EDTA titrant. So I'm going to set this up. You can do this several different ways, as I've mentioned in previous steps. This is really no different than what we've done in acid-base systems. I'm going to set this up using that sort of ratio formalism. So I'm going to take our volume at equivalence, which is 25, subtract the amount that we added here, the 5 mils, and then divide that by the volume at equivalence again. This will tell me what fraction of calcium I have left in the system, right? So just to be clear here, this is volume at equivalence, this is volume at equivalence, and this was the volume added. So this will tell me that I have 20/25ths or 4/5 of my calcium left in solution, which I then need to multiply that by the original concentration of calcium in the system, which was 0.0400 molar. And then I need to multiply this by my dilution factor here, which in this case is going to be my 50 mils that I started with of the calcium solution divided by the 55 mils. And so if you're trying to remember what that means, really this first step is just a fraction and it's unitless. And so multiplying that fraction by the original concentration gives me the fraction of concentration that exists. Multiplying by the 50 mils gives me the number of moles of calcium in the system at that fraction, and then dividing by that final volume gives me the moles per liter again. So really those are the steps. You could write this out dimensionally. It'll get you the same answer. This is just shortcut. So I'm going to write this down as the initial calcium, or the formal concentration of calcium, and then this first value here is our V naught, that's our original volume, and then this is our total volume. So exactly the same setup that we've done as one of the methods that I showed you for acids and bases. So if we compute this, this gives me a calcium concentration at this point where it's in excess of 0.0291 molar, and then to get to P calcium, I take the negative log of this value. So I'll just write negative log of that value, gives me this value, P calcium, which is 1.54. I'm not being very cautious with sig figs here, so don't think that I'm necessarily holding true to things. That gives me 1.54. So what I'm going to do is delete our sort of placeholder, and then I'll write up our own so we can keep track. Okay, so the curve or the plot looks something like this. So we just computed for 5 mils. So on our x-axis we have mils of EDTA. I drew up 25 here because that's our volume at equivalence. We don't yet know what the P calcium is there, but we do know that that's going to be the inflection of our curve. And then at 5 mils, we calculated 1.54. So somewhere in this range is where our first data point is. Okay, so next point on the curve is at the equivalence point, and we already determined the volume at equivalence, which was 25 milliliters. As always, I'm going to ask you at the equivalence point, what do we have in solution? So let's pretend, let's just write up our original expression here. So we had calcium plus, and we're adding EDTA, and we're sort of by convention assuming that's in Y4 minus form, and that's in equilibrium with the complex calcium Y2 minus. So the definition of our equivalence point is that we've added exactly enough of our Y4 minus, our complexing agent, EDTA, to completely complex out all the calcium. So that means we've completely converted all the original free calcium into the complexed calcium Y2 minus form. So this is what we have in solution at the moment that we've added all of our EDTA. Well, what's going to happen? This thing is going to it's going to fall apart. It's going to dissociate, and this equilibrium is going to trickle backward by some very small amount. So we're going to use this expression. We'll have just a little ice table and account for, well, how much calcium Y2 minus, how much of the complex did we have at the start of this initially. And then, so we'll have something that looks like this, or IE or ice or whatever you want to do. We need to figure out what is the initial concentration of the calcium Y2 minus. Well, it should be equal to the formal concentration of calcium 2 plus, except we've added this new volume, so it's going to be diluted a little bit. So to compute, we'll just do it over here, to compute our calcium Y2 minus, and I'll put 0 here for our formal, our initial concentration of the complex, that's going to be equal to the original concentration of calcium, our formal concentration of 0.04, so it'd be 0.0400 moles of that per 1,000 mils, and we had 50 mils of it, and then so that gets us moles, and then we divide that by the total volume, which would have been 50 plus 25, which would be 75 mils, 75 mils, and then we need to convert this by converting mils back to liters. So I'm running out of room here, but you get the general premise there if I don't write it out completely. That gives me a value of 0.0267 molar, so I'm going to put that in for my initial concentration of the complex, and I'm going to assume that I have 0 of both of those species right at the initial period where I've added exactly the right amount of EDTA. And then, of course, this is going to proceed to equilibrium by falling apart or dissociating a little bit as dictated by our conditional formation constant here. So that means at equilibrium, this will be 0.0267 minus x, and then some x. Each of these will be present in the system. So I'm going to set up the original complexation reaction in an equilibrium expression, set that equal to K prime F, which we already computed as 1.34 times 10 to the 10. And so that simplifies to 0.0267 minus x over x squared. So we can solve this system for x. So I didn't do a quadratic. Instead, what I did was just assume that this x here was tiny, simply because we have a really massive kf pushing us in the complex direction. So that's 10 to the 10. So my thoughts would be the reverse of this are going to be 1 over that, which would be 10 to the minus 10. My thoughts would be that this x then would be, or both of these x's would be inconsequential. In other words, this x here, if we're subtracting something that's in the minus 10 range from something that's in the sort of minus 2 range, that is inconsequential, especially within the number of significant digits we're trying to conserve. So I set that to 0, where I said it was essentially 0, and solve for x. That gives me an x, which is equal to calcium concentration here of roughly 1.4 micromolar. Okay, so taking the negative log of that value, and that gives me 5.85. So I can go up on my curve here. This is where my VE is, my volume at equivalence. This is just below 6, so we'll say that's where my inflection point is. I can check my approximation really quick too, because remember the approximation is that x is so small that I don't need to subtract anything from the 0.0267 value. So what I do is just subtract x from the 0.0267 value. And in this case, the value is on the order of 10 to the minus 6 range. So that means I'm subtracting a value out. So this would be 1, 2, 3, 4, so 5, 6. So I would only be changing this digit in the value, and we're only holding 3 sig figs here. If I were holding 5 sig figs, it would become consequential, but I'm not, and so this approximation holds true. Again, the sort of when to use approximations, it's up to you. That's really the intuition that you're learning and developing in this course. I'm just telling you how I went through this problem. You could have solved this with the quadratic and not even question this or considered this. It's completely up to you, but in this case, that approximation holds true. All right, so the final region here is the one where we have excess EDTA because we have added enough of the EDTA volume that we're past the equivalence point. So as an example, we'll say 1 mil past equivalence, and that would equate to 26 mils since our equivalence volume was 25. So in that case, we need to compute what our EDTA concentration is because it's in excess here. We'll do this just like we would have done the calcium concentration, where we take our original volume, which would have been not volume, but concentration, 0.08 molar EDTA, and then we're going to multiply that by our excess volume of EDTA, which would have, I could write this out, this would be 26 minus 25, so that's 1 mil. Multiplying this gives us the number of moles of EDTA in excess at this point, and then dividing that by the total volume of the system. In this case, this would be the 76, because it would be 50, my original plus 26 mils. That would give me then the new concentration of EDTA in the system. So that gives me 1.05 times 10 to the minus 3 molar. That's my excess EDTA concentration, but I'm trying to get to my calcium 2 plus concentration at this excess because we're trying to compute P calcium. So at this point in the titration curve, because we've added excess EDTA, we can assume that we've complexed all of the original calcium ion in the form of the complex, and that's calcium I2 minus in this case. And so at this point, what we can do is compute what the concentration of calcium Y2 minus is in this new volume. So essentially what we're doing is taking the formal concentration of calcium, saying, well, it's all now converted into calcium Y2 minus, but we've got a new volume. So we'll compute that. The assumption here, the approximation, is that none of the calcium Y2 minus breaks apart, and that's a fair approximation. We know that not to be true, but what we just literally computed is at equivalence, only about a micromolar of it breaks apart. And so when you're talking about excess EDTA in the millimolar range, that becomes inconsequential. And so we're just converting our formal concentration into a new or adjusted formal concentration. So that's going to be our 0.0400 molar that comes from our original calcium concentration, and then multiplying that by our original number of mole, or original volume, which gives us the original number of moles of the calcium complex without any additions of titrant, and then we divide that by our total volume here. So very similar. That gets us a value of 2.63 times 10 to the minus 2, oop, not 3, 2 molar. So that is the new concentration of calcium complex, because we've driven that reaction. So just to be clear, we've taken calcium 2 plus, we've added a whole bunch of excess of this stuff, and we've driven it all into this form, and then we just computed, since we knew the original concentration of calcium and we knew it all has to be in this form, we just divided it by its new volume, which is the 50 plus 26. And so now we have what the calcium Y2 concentration is under these conditions after we've added 26. And so the last step here then is that we know the equilibrium concentration using the adjusted Kf value is going to be equal to our calcium Y2 minus divided by calcium 2 plus divided by EDTA concentration. We know this value, we know this value, and we know this value. So you can plug those values in and use our original Kf value, which was that 1.34 times 10 to the 10 here, and we can solve this for calcium. That gives us a 1.9 times 10 to the minus 9 molar. I'm not going to write it all out because it's plug and chug, but just know that any region where you have excess EDTA, the steps required to compute that, you're going to use our normal equilibrium expression for Kf, but you're just going to compute the new EDTA and complex concentrations for the new volumes. That's it. And then you're going to plug and chug to compute calcium 2 plus. So that means that the P calcium for this step would be negative log of that value. So the P calcium in this case, let's just write it up. P calcium, negative log of the 1.9 times 10 to the minus 10 gives us an 8.72 value. So I just grabbed on our curve here, roughly 9 here, and at roughly 26 there. And so the general shape of the curve then becomes very similar to what we would see for a strong acid, strong base titration, where you have a really sort of flat area and then a very aggressive asymptote, and then it comes back up and plateaus out again when you have excess. So this is an example. You have all the tools. Really, the tools aren't any different except for maybe this different notion of K prime F. In adjusting that and using the fractional coefficient alpha to deduce that. Everything else, mechanistically, once you sort of learn that that's a nice trick to use, saves us a lot of work, everything else mechanistically is identical to, say, a strong acid, strong base titration. We're just accounting for what's in solution at any given moment in time.